Welcome to CEC lectures. Myself Dr. Preeti Jagwani from Department of Computer Science, Aryabat College, University of Delhi. So in our previous lecture we have seen how page faults are going to be handled in case of virtual memory techniques, and today's topic is about thrashing, and one more sub module we will be taking, that is storage management. Now let us begin with the topic thrashing. So thrashing is, if I am going to define this thrashing or the concept of thrashing in a nutshell, this is basically a high paging activity. That means a high paging kind of, we can say, frequency. So now how this paging frequency increases. So let us try to understand the situation that we have multiple processes, because multi-programming is the system in which we are working in. So we have multiple processes, and any process, let's say, that is not having enough frames. So if the process is having shortage of frames, what it is going to do, it is actually kind of, we can say, it will quickly page fault, and it needs to support pages in active uses, and it is going to page fault very quickly. Now at this point of time, when the process is in requirement of some pages and enough frames are not available with the process itself, then the process is going to replace some pages. And what is happening within the physical memory is all its pages are in active use, but it is somehow it has to replace a page that is not needed, maybe presently, or will be needed assuming that it is not going to be needed very soon. But what will happen after some time, that page, because all of the pages are in active use, that page which is being replaced will be needed again right away, and then again your process is going to give you kind of, we can say, a signal of page fault, and again it is replacing pages, again and again it is bringing back the pages. So swapping in and swapping out is kept on we can say kind of quickly with very high frequency. So that kind of high paging activity is known as thrashing. So thrashing is some situation in which your system is spending more time in paging rather than execution. So let's say execution is happening for t amount of time, but the paging is taking t dash amount of time, where t dash is more than t. So this is what you call thrashing. Now what is the problem with this thrashing technique, or what is the problem with this process of thrashing? So thrashing, as I have told you, that it is a high paging activity, and system is more busy in paging rather than execution. So what is actually happening? Let's say there is a multi-programming scenario. If a CPU utilization is too low, then system is going to increase the degree of multi-programming and for increasing the degree of multi-programming, it is going to introduce a new process to the system. Now what will happen? Let's say our system is a kind of having global page replacement policy. So global page replacement policy, if you are able to recall, that it is something the page can be replaced from its own frames or any other frames or the frames of any other process, we can say. And presently our system is having this global page replacement algorithm. So it is going to replace the pages without regard to the process to which they belong. Now let's say a process enters in a new phase in its execution and need more frames. So it starts faulting and taking frames away from the other processes, while the other processes are in need of those pages which are being swapped out from which are being swept out through a particular process, and the other processes will also start faulting and taking frames from other processes. So what is happening? Let's say process 1 is taking a frame from 2, 2 is taking a frame from 3, and so on and so forth. So these faulting processes must use the paging device to swap pages in and swap pages out, and as they queue up for paging devices, the ready queue empties and the processes are going to wait for the paging devices, and somehow with this whole scenario, this CPU utilization is going to be decreased. Why CPU utilization is going to be decreased? Because all the processes are waiting for that paging device and none of the processes is available in the ready queue. That means none of the processes is available in order to kind of resume or start its execution. So, the ready queue is empty and processes are waiting for the paging device. So, if ready queue is empty and CPU is sitting idle, that means it indicates that CPU utilization is decreasing. Then what will happen? The CPU scheduler sees the decreasing CPU utilization. That means the scheduler is witnessing that utilization of CPU is decreasing. Now, what is the scenario when the CPU utilization is decreasing and the ready queue is empty? That means there are lesser than the processes which CPU can execute or CPU can process. So, your scheduler is going to increase the multiprogramming, increase the degree of multiprogramming as a result, and the new process is also into kind of we can say trap of paging in and paging out. That new process tries to get started by taking frames from the running processes, causing more page faults and a longer queue for the paging devices. So, what is happening? The newer process which came into the loop or which came into the system for in order to, let us say, increase the CPU utilization is also not able to help, because it is also getting into the trap of this paging in and paging out activity. So, as a result, what is happening? Ultimately, your CPU utilization is going to drop even further, even if your CPU scheduler tries to increase the degree of multiprogramming even more. So, thrashing is kind of occurring and the system throughput is totally we can say plunging, and the page fault rate is increasing tremendously. Almost each and every process is kind of throwing many page faults. As a result, the effective memory access time increases and ultimately no work is getting done, because your system is all busy in paging, in swapping in and swapping out. It is not doing any execution. The processes are spending all their time in paging activity. Now, what happens in case of thrashing? How it is going to affect the performance of the system, that can be seen on the screen with the help of a figure. So, on the y axis we have CPU utilization and on the x axis we have degree of multiprogramming. Now, what is happening? In order to increase the CPU utilization, the degree of multiprogramming is being increased, and hence there is a curve which is increasing towards the which is increasing both ways. That means it is increasing on the x axis, and also it is increasing on the y axis. But with a particular point of time where the kind of we can say arrow of thrashing is we can say starting, or arrow of thrashing is beginning, that is the point where thrashing or where the process of thrashing has been kind of we can say started into the system. And what is happening here is, now if further degree of multiprogramming is being increased, now if anything on x is going to increase, this is going to have an adverse effect on the CPU utilization. That means now increasing the degree of multiprogramming is not going to increase the CPU utilization. On the very other hand, it is going to decrease the CPU utilization, and that too kind of very sharply we can say. So, you can see the curve here, it is increasing in both the directions. I can say it is with the degree of multiprogramming, the CPU utilization is increasing, but after a particular point of time, if the CPU scheduler is increasing this degree of multiprogramming further, it is going to give you a dip in case of CPU utilization, and this is what the situation of thrashing is, which I have just explained. So, this is the effect of thrashing in when we talk about CPU utilization. So, with this we are actually we can say we have covered almost all the topics in case of virtual memory, what we are talking about, and thrashing also we have seen in this lecture. Now, moving towards our new module, which is about the storage management. Now, the moment when we are the moment I am talking about term storage, what is we can say coming in the mind. So, we have some mass storage devices. In terms of storage, we have we can say our random access memory, that is the first term that comes into the mind, or we have other mass storage devices also. So, here in this topic of storage management, we are not going to talk about anything which is related to physical memory or random access memory. We will be talking about our secondary devices, which are it could be a magnetic disk, it could be a magnetic tape, and it could be a solid state disk. So, with this concept of mass storage in context of operating system concepts, we are going to see that how these storage devices are being managed in order to we can say have the maximum utilization or the optimum efficiency of a system. In order to understand that thing, let us try to first we will see the structure of a magnetic disk, or we can say the structure of our hard disk, which we we can say very regularly use it. So, the figure which you can see on the screen is showing that structure. Here you can see there is an we can say a complete structure with one of the arm assemblies. There are these metallic disc which are arranged on the on an spindle, and these metallic discs are we can say these metallic discs rotate, and this whole assembly is actually packed in a metallic container. Now, here what is happening, if you can see around this spindle, these CD kind of metallic discs are rotating, and your whole data is being stored on these metallic discs. In order to read and write the data, there are read and write heads. If you can see on the screen, there are separate read and write heads for each and every a metallic disc. We can say there is a read and write head for the metallic disc the upper front, and there is a read and write head for the lower front also. So, here we have arm assembly through which all these read and write heads are connected, and these magnetic these we can say these discs are actually moving at a high speed, and read and write heads are responsible for reading the data or writing the data. Now, how this is being kind of read or write. So, here in terms of location, when we talk about, we have with on these different platters, on these different discs which I was saying, on these different platters we have virtual we can say partitions which are in the form of tracks, which are in the form of sectors, and there are also cylinders. So, now let us try to understand what are these tracks and what are these sectors. So, we have flat circular shaped platters like CDs, whose diameter ranges from 1.8 to 3.5 inches, anything from 1.8 to 3.5 inches of diameter these plates can have. These surfaces of these plates are covered with magnetic material, because the reading and writing of data is going to actually happen with the help of magnetization of that particular surface. Now, it is going to store the information by recording it magnetically on the platters. Now, coming to the partitions, or coming to the divisions, we have divisions in the form of tracks, we have division in the form of sectors, we also have the division in the form of cylinders. So, the surface of platter is logically divided into circular tracks. So, those circular linings are actually various tracks which are definitely numbered. and these tracks are divided into wedge shapes structure which are known as sectors, and the set of tracks that are at one arm position makes up a cylinder. So, in order to understand the concept of this tracks, sectors and cylinder, let us see this figure once more. So, all these circular structures are basically tracks. Then within those tracks there are divisions which are wedge shaped divisions, and these wedge shaped divisions are nothing but sectors, and there are cylinders. That means many of the tracks comprises of one cylinder. So, the cylinder, sector and track all you can see here in this figure. Now, what is happening next? There may be thousands of concentric cylinders in a disk drive, and each track may contain hundreds of sectors. So, you can imagine the level of we can say minute level on which all these things are being implemented, that thousands of concentric cylinders in the disk drive, and each track is having hundreds of sectors also. Coming to what is going to be or what kind of storage capacity is common in the disk drive. So, as you are aware, gigabytes and nowadays terabytes also is a very common storage capacity. When the disk is in use, a drive motor spins at a high speed, and with this this whole we can say platters are going to spin, and what is the speed of spinning is 60 to 250 times per second. So, speed is kind of we can say very high, which is 60 to 250 times per second, and common drives which are very commonly available and which we also use in our systems, they spin at 5400, maybe 7200, 10,000 or 15,000 rotation per minute. So, per second rotation varies from 60 to 250, while the rotation per minute is ranging from anything from 5,000 to 15,000, and that is a very common speed. That means we can say this whole all these platters are spinning at a very high speed. Now, disk is the speed of disk which we were just discussing has two parts. One is the transfer rate, and another one is known as positioning time or the random access time. So, the transfer rate is basically the rate at which the data flows between the drive and the computer. Or for example, let us say we are talking about there is a file which is to be opened, that means that will be taken from the drive and that will be we can say stored into the physical memory. So, that is what we are saying here as a computer. So, the transfer rate is the rate at which the data flows between the drive and the computer, while the second part of the disk speed is again we can say divided into two parts. Those two parts you can see on the screen. One is the seek time and another one known as rotational latency. So, now this disk speed has two parts. One is the transfer rate, as I have told you, the data flow between the drive and the computer. The second part is positioning time. So, as the name indicates, positioning time is the time taken by the head in order to position itself on the particular data which is to be read. And now that data is actually we can say available on different sectors, on varying sectors and on varying cylinders and on varying tracks also. So, now the positioning time is consisting of two parts. One is the seek time and another one known as rotational latency. Now, we will be seeing that what do we mean by seek time and what do we mean by rotational latency. So, the time required to move the disk arm to the desired cylinder. I have told you that there are thousands of cylinders, and these cylinders are actually we can say are in the form of those pack of those concentric circles which are known as tracks. So, in order to move the disk arm to the desired cylinder, that particular time, let us say for example, on the cylinder which is having a number 200, the data is stored on that. So, that time is known as seek times, which is required to move the disk arm to the desired cylinder. A time necessary for the desired sector to rotate to the disk head, that means that sector these platters are rotating, and let us say the disk head, that particular sector is here and here is my disk head, then there is some time which is this sector is going to take in order to travel from this particular point to this point which is under the head. So, the time necessary for the desired sector to rotate to the disk head is known as rotational latency, and rotational latency and seek time together are basically known as positioning time. So, after positioning, your data is being read and now that data is being sent to the memory or sent to the system, we can say. So, that time is also that time is known as that is the transfer rate, while some time will take into the some time will be taken for positioning. Now, if we talk about the what is the transfer rate or what is the amount of data which can be transferred. So, typically we can say that disk can transfer several megabytes of data per second, and they have the seek times and rotational latencies of several milliseconds. So, seek time and the rotational latencies are of order of milliseconds, while the data or the amount of data which can be transferred goes up to several megabytes of data per second. Now, with this structure, we have seen what actually your kind of disks are, magnetic disks we can say, and how do they operate. So, basically the the disk head files are on an extremely thin cushion of air. So, what I am trying to say here is these platters are having very minute extremely thin space between them, and there is always a danger that the head will make contact with the disk surface, which is not desirable at all. After all these disk platters are coated with a thin protective layer, even if there is a layer which is kind of we can say protective layer in order to protect the platter from getting scratched or getting crushed, the head sometimes damage the magnetic surface, and this phenomena is known as head crash. So, basically because of where is a some micron of the space or some micron of the length is between the head and the platter, there are chances that head is going to damage the magnetic surface, and this kind of damage is known as head crash. Now, this head crash, if it happens in the disk drive, it cannot be repaired, then in that situation the entire disk has to be replaced. Now, with this we also have nowadays it is also common to have removable disk, a disk which can be removed and mounted onto the other systems, or allowing different disks to be mounted as needed. So, removable magnetic disks generally they have only one platter, and the example or the best example of the removable magnetic disk is your CD, or it could be your DVD, or it could be your Blu-ray disc and Blu-ray disc, as well as removable flash memory devices known as flash drives, which are a type of solid state drives. All these CDs, DVDs, Blu-ray disc and removable flash memory devices comes under the category of removable disc. So, basically removable magnetic disc generally consist of one platter, although it is not a hard and fast compulsion. They are held in a plastic case to prevent damage while not in use. Now, how the data is being transferred from this drive to the system? A disk drive is attached to a computer by a set of wires, and that set of wires is known as input output bus. there are several kinds of buses available which are having different technologies of data transfer. These we can say buses are advanced technology attachment ATA. They can have it can have SATA, which is serial ATA, commonly known as SATA. Then eSATA is also one of the bus, or USB. We all use USB buses, which our pen drives are basically connected on these USB ports, and we also have fiber channels. So these are basically kinds of buses which are available for data transfer. Now these data transfer on a bus, how these are going to be carried out? These are going to be carried out with the help of some special controllers. So I will be taking the topic of controllers in detail in our upcoming lecture. Meanwhile, let us recap the lecture. So here we have started with the concept of thrashing, and we have seen the performance degradation as a result of thrashing, and then we started with the storage management concept. And before going into the technical before going into the operating system level details of storage management, we have understood how all these disks are being working, and data transfer, how it is going to take place, that we will be taking up in the next lecture. So here is a list of references which is being prepared, which is being used for the preparation of lecture. Hope you have enjoyed. I'll see you in the next lecture. Till then, goodbye, take care.